Thanks for the introduction. This is a joint work with Rupak and Philip, who is also here, from Max Planck Institute for Software Systems, and Mitra and Georg from Vienna University of Technology. So as already motivated by the previous talk by Ankush, coming up with reliable distributed systems is difficult. They are complex systems with many sources of non-determinism. Distributed nodes communicate each other by exchanging asynchronous messages whose ordering is non-deterministic. Unexpectedly, some nodes might crash and reboot. And there is some data replication going on between the distributed nodes for fault tolerance. And all these nodes serve to multiple clients concurrently. All these things can lead to some bugs that are difficult to reproduce and diagnose, which expose only in certain interleavings of certain events. So if you have a look at the issue tracking pages of popular distributed systems, you will see many bug reports, which end up some write failures or written inconsistent data between nodes and so on. So the question is how to detect such bugs. And an idea is systematically testing all possible executions of the system, which is infeasible. Even if we apply some reduction techniques, still the number of executions to explore is huge. A practical and commonly used in practice approach is random testing. It is shown to detect some bugs, but it provides no guarantees. So our contribution in this work is to provide a randomized testing method, which we call PCTCP, with probabilistic guarantees on detecting, which gives some lower bound on the probability of detecting a bug for distributed message passing systems. I'll start with a simple example to show how our approach works. So PCTCP stands for probabilistic concurrency testing with chain partitioning. As the distributed program executes and produces some events, we maintain a partially ordered set of them. And at the same time, we decompose this partially ordered set of events into causally dependent chains. So in that example, we have three nodes, handler, logger, and terminator. When handler takes a request message, it sends a log message to the logger to log some data, and terminate message to the terminator to terminate the system. And when terminator gets the terminate message, it sends flush message to the logger so that it deallocates some structures and buffers. And when logger is done, it sends flushed message. So in that program, if the logger first executes log and then executes flush, everything is fine. But if it first executes flush message, deallocates, and then tries to log data, then we have a bug. So here, let's see how our method works on that. So initially, we have this request message in the poset. And we put it into a chain, which has only a single event, which gets to be scheduled. And when we schedule request, the program produces two more events, log and terminate, which are both causally dependent on request. Hence, we have these errors. So the events in the poset, which doesn't have any predecessor-successor relationship, are concurrent to each other. And we built the online chain partitioning. Here, let's say that we appended log message in the same chain with request. We cannot append terminate to the same chain since they are concurrent, and we create another chain and put it there. Now we can continue executing either with log message or terminate message. PCTCP assigns initially random priorities to the chains. So let's say that priority of C1 is greater than C2. Then we schedule log message. No more events are introduced to the poset. Then we schedule terminate. Flush message gets produced, and we execute flush and flushed. So now let's consider the other scenario where the priority of chain 2 is higher than the priority of chain 1. In that case, after request, we would continue by scheduling the events in C2, which are terminate, flush, and flushed, and then we would execute log, which would hit the bug. So as you see, PCTCP detects this bug with the probability of 1/2, while a naive random walk would catch it with a probability of 1/4, because each time there are two concurrent events, it would select either log or terminate. We go with terminate, and in the second one, we should go with flush. In general, distributed systems have many possible executions. So just for a simple case, consider n concurrent events, which has n factorial number of executions in total. What we want to come up with is, given whenever we produce a random test, we want to give a lower bound on the probability to detect the bug. And here, the key is the notion of bug depth. A common notion of bug depth is a minimum sequence of events which are required to expose the bug. For instance, if we are concerned with reorderings of only 2 events, such as the previous example with log and flush, then we are talking about this 2 tuples of events. If we are talking about the reorderings of 3 events, such as the case with atomicity violations, then we can capture more complicated bugs. And as D gets increased, we can capture more and more complex bugs. It's shown that in distributed systems, many bugs are deep bugs, which mean that to expose, they require many events to be interleaved. So if one wants to cover all depth D bugs, detect all depth D bugs in a program, then he has to cover all of these depth D schedules in their tests. And our notion of coverage is strong D-hitting families of schedules. So given a tuple of events, a schedule alpha strongly hits that tuple of events if for all events in the poset, if that event is scheduled later than one of these events in the tuple, it is because either that event is larger than this event or another event in the tuple which comes after that event in the tuple. So intuitively, it means that keep that order as much as you can, but also schedule them at the last moment in the schedule as possible. So just to get the idea, here are 2 schedule examples. And here is a poset. In the first schedule, strongly hits the event G because it is scheduled as late as possible, and also 2 tuple E and G. So E and G preserve their order, and they are scheduled as late as possible. And similarly, that schedule strongly hits the event E, pair GE. This time G is scheduled before E, and DGE. You see F has to go in between because F is causally dependent on D. So a strong D-hitting family is a family of schedules such that it has a schedule for hitting each D tuple of events. And the idea is we should sample from that strong D-hitting family of schedules. But it is difficult for distributed systems because the events in the distributed system are not known upfront. They are upgrowing and revealed during the execution. It is also dependent to the schedule. So I have a couple of events. Depending on what I schedule, I receive the events that are mutually dependent on the schedule and revealed online in the execution. So how to sample from the strong D-hitting family? We will use combinatorial results. Let's have a look at realizer and dimension of a poset. So realizer of P is a set of linear orders such that the intersection of these linear orders gives us the poset. And here is such a realizer. This is the partial order we've seen before. And the intersection of these 3 linear extensions gives us the poset. And the dimension of P is the minimum size of a realizer. Here it is 3. So if you see that since their intersection gives us the poset, actually this realizer covers all pairwise orderings of the concurrent events. So a question is, can we make use of the realizer of posets to generate these orderings of D tuples of events? And actually, there is a nice result by Fastener and Klo, which shows that online dimension and online adaptive chain covering, online width of posets are closely related. So we can treat those algorithms as 2-player games. So the first player is the program, revealing the events and the dependency relation between the events, one by one. And the adaptive chain covering decomposes these events online into a number of chains. And for computing linear extensions, here, given this decomposition into chains, here we generate the linear extensions of the poset. Let's see on an example. So first we have A. So the online chain covering puts it into a chain A. And online dimension algorithm associates each chain to a linear extension, where in that linear extension, we put the events in that chain, we append them to the end of the linear extension. So it is trivial here. When we have D is in C1 associated with L1, so we just append D. When we have B, since we cannot append it here, we have a new chain and a new linear extension associated with that chain. And in that linear extension, first we copy one of the linear extensions at hand, and B is appended at the end in L2. And in the other linear extensions, we push B to the beginning as possible. Here it is the first event. And E is appended to L1 and added as early as possible into L2, which can come only after D here, since due to the causal dependency. And for C now, we have an additional linear extension. We copy one of these linear extensions and append C to the end and push back C in the other extensions. And F is dependent on both D and B, but can't be appended here. So we append it here, and similarly, we can generate the realizer. So if you have a close look at this linear extension, what we built is actually a strong one-hitting family, where we have a schedule which strongly hits the events in the associated chain. This result is not stated in that manner explicitly in that paper, but what is built is the strong one-hitting family. So our main result in that work is that we extend it, and we say that, we observe and show that the optimal size of strong D-hitting family is bounded above by the optimal number of chains we can have by adaptive chain covering algorithm times n choose D minus 1 times D minus 1 factorial, which comes from this schedule indices. So we do this by indexing the schedules in the strong D-hitting family by that schedule index. Here, lambda is a chain ID, and so this is selected from one of the chains in adapt W, which is the width of the poset of online width of the poset of width W. And we select D minus 1 events among n events, and we want to cover all possible orderings of them, and hence the factorial. So for these indices, each of these index strongly hits all the events in the chain alpha and the D minus 2 events associated by these n's. Since we don't know the events before the execution, here we cannot quantify over the events, so we use an event labeling, which chooses us these events to be singled out. So how we enforce this in the execution? Actually, we want to sample from that set of schedules which are indexed by this. So we create a random schedule index, and by assigning the random initial thread priorities, actually the lowest assigning chain priorities, the lowest priority chain is the lambda chain, because the events in that chain would be strongly hit. And each time we see in the execution an event which is labeled to be singled out, we update the thread priorities so that the chain which has the singled out events next will be executed later to preserve the ordering of these D minus 2 events. We experimented on three sets of frameworks and systems: P# framework, Cassandra, and Zookeeper distributed systems. You can have a look at the source code in the given links. Here I'll only show the results for the Cassandra. And what we detect is that bug actually I showed in an earlier slide, which executes 3 concurrent client requests and requires reordering of many messages. So we tested the system with different number of event labels, 4, 5, and 6. And we couldn't find any bugs with d equals 4. But with d equals 5 and 6, out of 1,000 runs, we could catch the buggy execution in one execution. But in random walk, out of 1,000, we couldn't expose the bug. That might be explained by the average number of available messages or chains at a given time. So with random walk, it's higher, but the maximum number of enabled chains are smaller in PCTCP. For Zookeeper, we also modeled node crashes and node reboots. So how we modeled is that after each start of a node, we appended a successor crash event. And after each crash event, we appended a successor start event. And we executed such events up to a given budget of crashes and reboots. In our experiments, we used 1 for both. And we could hence model these events, and then on the poset, we can schedule them as the other message send events. Our results extend 2 lines of works. So the first one is PCT for multithreaded programs by Sebastian Burkhardt et al., who is here. So here, PCT, probabilistic concurrency testing, works on multithreaded programs where the events are actually totally ordered chains, linear orders. And there, the probability of hitting a bug is 1 over k times n to the power of d minus 1, where k is the number of threads. And that's that is the same with our probability. So we detect the bug with a probability of at least that number, because the size of the hitting family is smaller than that number. And you see the number of chains we can obtain in adaptive chain covering correspond to the number of threads in the multi-threaded setting. And actually, I didn't include in the slides, but the optimal size of optimal number of chains for the online width algorithm is w squared. So it is the probability boils down to 1 over w squared times n to the power d minus 1. And it also extends the results of d-hitting families of schedules by Dimitri, Rupak, and Philip. Here, that work generates the hitting families of schedules, which generates reorderings of d-tuples of events for the programs where the events form a tree structure. So our method, different from that, applies to any a partially ordered set of events with any structure, and also an upgrowing poset. So to wrap up, we proposed a randomized testing method, PCTCP, with probabilistic guarantees for distributed systems. And how we do this? We randomly sample from strong d-hitting families of schedules. We used combinatorial results on dimension theory and adaptive chain covering. We indexed the schedules in the family by using the schedule indices, and showed that the size of the strong hitting family for a poset with W and the number of events n is smaller than this number of chains times n to the d minus 1. And we said that this generalizes the guarantee provided by PCT for multi-threaded settings. In the paper, you will see the formalization for online hitting for upgrowing posets and online hitting for scheduling posets, which actually encode all possible ways the program can extend the poset and the scheduler can build the schedule. And you can also find our experiments on P#, Cassandra, and Zookeeper. Thank you. I'm happy to have your questions.
Thank you. Questions? Don't be shy. Front row.
So your comparison point was with respect to random walk, right? And
Yes.
can you give, like, what exactly did you do for the random walk? Did you do like bounded depth, or did you bound the number of uh, uh, in your case events or message types with? I mean, in the sense, you said that one of the reasons why random walk would not work is that it has a larger width, average width.
Yeah,
What
this
if you
is what
bounded
we
that
obtained
average
in
width
that.
to be 5 and then approached and applied random walk? Would it perform as PCTCP or?
No, we didn't bound anything in random walk. So it's just we started executing. And random walk, at each time, we have a number of concurrent events which are enabled. It blindly selects one of them and continues execution. So it selects only from the concurrently enabled set of events without any bounds.
You didn't even bound the length of your executions.
No, we didn't. Here, it's in that example, especially, for instance, there are these 3 client requests and a number of distributed system protocol executions. So the number of events were already bounded in a way.
Hi, Grey Walk. I have a question about what's the scalability for a very complicated system. How will it scale well? You have
scalability.
Yes, for a large system.
So this is actually scheduler-based testing. So once you hack into the scheduler and you have the control over the events, then in terms of performance, are you asking? Because the method applies to any size of the program, but it requires the programmer to provide a maximum number of events in the system. And the probability of hitting the bug is dependent on that. So maybe in terms of scalability, I can say that it requires the maximum number of events to be given should be close to the actual number of events in the system for theoretical results. For implementation part, I don't see a scalability problem.
Any last quick questions? Yes.
Hi, this might be a bit of an applications or out there question, so bear with me. In databases like Cassandra, sometimes the consistency models they expose are slightly less strong than we would want. You could view that as the user accepts a probability of a bug from that consistency model in exchange for speed. Do you think that your probabilistic technique could give us a better idea of exactly what the probability of a bug we just accepted is?
For a given consistency model,
Yeah.
You're asking.
And a given application working against it.
Here we consider the system as a black box which can use any consistency model actually. So we are not specifically examining what is the consistency model and delaying or preventing messages for that. So we don't do a specific analysis for that.
Okay, let's thank the speaker one more time.